Hi, my name is Chris McClendon. I'm a consulting geologist in Mandeville, Louisiana. I want to give you a very brief summary of comments submitted on the environmental impact statement for the Mid-Barataria Sediment Diversion. Primarily want to relate those to the surface fault traces, which are constantly evolving with university research and inputs. We'll look specifically at a few of these for information, but it's important to note that there is a constant movement of the surface of the Earth, both vertically and horizontally, a significant portion of which is associated with these faults. These are measured by the continually operating reference system, which is connected to the GPS network. We get up to 7 millimeters a year of velocity, of vertical velocity, and 3 or 4 millimeters of horizontal velocity. Taking a perspective look at this, we can draw a profile across South Louisiana and see the faults represented in the subsurface by vertical displacement of the sedimentary layers and thickening across the fault, and then the extension and often extrapolation of the faults to the surface to surface expressions of varying degrees of quality. But there is a contribution of downward movement associated with the fault and a lateral sliding basically toward the center of the Gulf of Mexico overall. And we'll be specifically looking at the Ironton Fault, which crosses the side of the Mid-Barataria Sediment Diversion. This is the surface trace of the Ironton Fault. We'll be relating it to 3 other faults, the Vacherie, the Highway 11, and the Gentilly Fault. The Vacherie Fault is the best expression we have, evidence we have of a distinct fault slip event within recent history. This happened between April 12th and 15th of 1943 at Laura Plantation near Vacherie. 8 inches of vertical displacement at the surface. Harold Fisk was dispatched by the Corps of Engineers to investigate. He took this boring profile across the fault and significantly measured 3 feet of vertical offset at the Pleistocene surface. Given that there's 8 inches of offset in the most recent event, the 3 feet is considered to be a cumulative effect of multiple fault slip events, and Fisk noted a potential relationship between these fault slip events and historical crevasses of the river. So certainly something that needs to be investigated in much more detail. The Highway 11 bridge fault is significant in 2 reasons. One, it's the best example of a high resolution seismic profile we have in South Louisiana. This type of detail, it's interpreted by John Lopez, allows us to see thickening of the individual sedimentary layers across a fault. If we had very accurate dating of these sediments, we could get some significant insights into the rate of fault slip over time. But we can get some indications here, at least in the recent past, from Michael Hopkins' presentation at State of the Coast in 2016. Total average rate of about 3 millimeters a year of displacement on the fault. But also importantly, if you look at the elevation across the hanging wall of the downthrown side relative to the upthrown, the entire span of the hanging wall has a lower elevation than the footwall, meaning potentially as much as 100 square miles was affected by the downward movement of this fault. The Gentilly fault was also interpreted by Fisk in the same report as the Vacherie fault. Took a boring profile in New Orleans East, displacement of sedimentary layers across the fault, 20 feet of displacement at the top of the Pleistocene. So implicitly a cumulative effect of some higher magnitude or possibly more frequent fault slip events, and also thicker accumulation of organic soils, what he called the humus zone, on the hanging wall of the fault. This can be compared to the map by Gould and Morgan of the thickness of peat across the New Orleans area, and the thickest deposits by far are on the hanging wall side of the Gentilly Fault across the central wetlands unit. Their profile showing that thickness of peat, and this is well known to be an epicenter of subsidence. No better representation than John Snell standing on Old Paris Road, which was built in the 1930s and now about 2 feet below the surface. Moving to the Ironton Fault, the best way to represent it is through standard oil and gas industry geology mapping techniques. One is a seismic profile across the fault. The subsurface trace, the interpretation can be seen by the offset of the seismic horizons and can be reasonably extrapolated to a surface trace. The fault can also be seen in the wells by correlation of the oil and gas wells. So the red numbers are the interpreted fault cuts, as they're called, in the wells. Take a profile of these wells across the fault. You can see displacement of the biostratigraphic horizons. These are representative dates in million years before present. So this is between the Pliocene and the Middle Miocene. And the throw of the fault is cumulative over time, so it's continually increasing. Classic South Louisiana growth fault, up to nearly 1,000 feet of throw at 11,000 feet depth. But if we look at the interval thicknesses on the hanging wall, footwall or upthrown side versus the hanging wall or downthrown side, we can compare the two to get an expansion index. And this is a standard evaluation process for looking at the history of fault slip over time. The expansion index on the Ironton fault shows sporadic changes in the rate of slip over time, but by far the biggest fault slip events were in the Middle Miocene, and this can be directly compared to deltaic deposition in the Miocene. And Doris Curtis gave us this excellent image of the interaction between sedimentary deposition in a delta system and fault movement here. So it's very important to note that throughout geological history, the deposition of sediments across a fault has the potential to trigger fault slip event. Looking in more detail near the surface trace of the Ironton fault, which is where you may expect any kind of response, that's the zero trace contour. It crosses the cone penetrometer test for the conveyance structure, and so we can look at a correlation of those tests along that, and an indication of 6 feet of displacement at the top of the Pleistocene. So this can be compared to the Vacherie fault, 3 feet here, 6 feet here. Fisk interpreted this to be the result of repeated recurrent fault slip events, creating a cumulative 3 feet. If this interpretation could be verified on the Ironton fault with high resolution seismic and sediment cores, as we have recommended, and it turned out to be 6 feet, that would imply there were either more frequent or higher magnitude events in the historical past here, and that would certainly be something important to determine. But by far, what we really need to do here is get some high resolution seismic across this and do the high resolution dating on the sediment cores and make some definitive determinations about the history of fault movement there. These were the recommendations our group, including Liz McDade and Dave Culpepper, made in 2017. I have reiterated them in a comment submitted last week on the draft EIS, and it's my hope that this type of evaluation will take place. Thank you very much for your time. Please feel free to contact me, and there's much more detail on this on my blog with a lot of backup on it. So thank you very much.